Okay, welcome to Chapter 13 in our physics class, where we're going to talk about temperature and the kinetic theory. We're going to start by talking about some basics about atoms. We're not going to get into a huge level of detail about the structure of atoms, but there are some basic things we need to know. The first is the idea of atomic mass. So atoms are incredibly small things, and so using something like a gram or kilogram to measure their mass, we would have to use very, very small numbers. So we've come up with this atomic mass unit that we abbreviate with a U, and it is based on the atomic weight of a carbon-12 atom. And it has a mass of exactly 12 atomic units. So one carbon atom has a mass of 12 atomic units. And if we equated that to kilograms, one atomic unit equals 1.6605 times 10 to the negative 27th. Think about that, negative 27th. That is very, very small. Okay, so that's the atomic unit, atomic mass unit. And then the next thing, like I said, we're not focusing on a high level of detail on the makeup of, excuse me, of atoms, the electrons and neutrons and protons, but we do need to, we're going to talk a little bit about the way atoms move around. So Brownian motion was detected when little flecks of dust landed on a surface of water. Someone named Brown, noticed that the flecks moved around in an unusual pattern, somewhat like this. And that just gave further credence to the idea that water is not just made up of water, but is made up of small molecules that are all bouncing off each other like pinballs. Okay, and so if we take that idea a little bit further, what we're seeing here, A, B, and C, are the three phases of matter, where we've got solid, liquid, and gas. And so at a molecular level, what's happening is that in a solid, the molecules are arranged in a nice, neat pattern here, in rows and columns. So we've got a nice row there and columns, and they they keep their shape, they keep their structure. In a liquid, they start bouncing around each other a little bit more. So this is how that our knowledge of this was in part developed by the observation of this Brownian motion, that when some dust particles land on the surface of the water, they're bouncing all around, and something must have been causing that to happen. And so turns out it's the molecules themselves in the water moving around and colliding with each other and bouncing apart. And then in the gaseous state, the molecules just move even farther apart, and they move with more velocity. And so if you remember, both liquid and gas are fluid, and solid is not. So a fluid will flow and take the shape of the container it's held within, and the solid keeps its own shape. So liquid and gas are pretty similar in the molecular level. It's really just a difference of how far apart are the molecules and how fast are they moving, how much energy do they have. Okay, so let's circle back around to the atomic mass unit, and we'll look at an example problem here. So again, we use the atomic mass unit U to measure the mass of an atom, and it's based on the carbon-12 atom. Carbon is made up, its nucleus has 6 protons and 6 neutrons, and so that makes a total of 12 subatomic particles in the nucleus, and that's what we base this off of, is the carbon. That's the basis. And 1 atomic unit is 1.6605 times 10 to the negative 27th kilograms. So if we had a cube, a perfect cube made of pure copper, and it was exactly 1 meter by 1 meter by 1 meter, so all sides of this cube are 1 meter, how many copper atoms would be in that? So we know the density of copper is 8.9 times 10 to the third kilograms per meter cubed, and a copper atom has a mass of 63 atomic units. Actually, we don't want to know how many there are. That would be a little bit of a simpler question. We want to know the distance between them. How far apart are they between one carbon atom and the other one? How far apart are they? That's a little bit more of a difficult question, but it's not too tough. Let's tackle it. So it kind of takes some creative problem solving here. So first of all, we know that the density of something is equal to mass divided by volume. How much stuff can we fit into a given size? And so if we solve that for mass, mass equals density times volume. And the density of copper was given to us as 8.9 times 10 to the third kilograms per cubic meter. And our cube is 1 cubic meter. And so the mass we're dealing with is 8.9 times 10 to the third kilograms per cubic meter. I guess I didn't need an end parenthesis there. Let me let's erase that. There we go. Okay, so that's pretty straightforward first step. We just determine the mass of this cube, 8.9 times 10 to the third. Actually, hold up, let me get my eraser back out, because I found the mass, not the volume. We knew, or not the density. We knew the density. Okay, so this is the mass of the cube we're dealing with, 8.9 times 10 to the third kilograms. So if we did want to know how many atoms there were, this is what I thought the question was asking at first, it would be that total mass, 8.9 times 10 to the third, that's the mass of the entire cube. If we divide that by the mass of one copper atom, that will tell us how many atoms there are. And if we look back at the original problem statement, we're told each copper atom has a mass of 63 atomic units. That's the mass of one copper atom. So the mass of one copper atom is 63 times an atomic mass unit in kilograms is 1.6605 times 10 to the negative 27th kilograms. So this is 63 atomic units. This is an atomic unit multiplied by 63. That's the weight of a copper atom, or the mass of a copper atom. We're dividing the mass of our cube by that. And so what we get is 8.5 times 10 to the 28th copper atoms. So that's a lot, right? Obviously that's a lot. we would expect that because atoms are very small, so we would expect there to be a lot of them. So here's where sort of the creative problem solving comes into play. What we have to do is sort of imagine, because this is solid, that it's arranged, excuse me, that the atoms are arranged in rows and columns. They're neatly stacked up here. And so if the, let's lay down some fundamental stuff here, that a cube, the volume of a cube, is equal to the length of one of its sides to the third power. Okay, so if that's true, then the length of one side of a column is equal to the third root of the volume, or we could write that as volume to the 1/3 power. So if we want to know the number of copper atoms, try to draw a cube here, along one edge of the cube, just right along that one edge, we could take the volume to the 1/3 power, or let's put it this way, the number of copper atoms to the 1/3 power. So there's 8.5 times 10 to the 28th copper atoms. That's how many there are, making up this whole cube. If we take that to the 1/3 power, that'll tell us how many copper atoms there are along one edge. And so that's 4.4 times 10 to the third. That's how many copper atoms there are along one edge. Well, if the edge of our cube is 1 meter, then we just have to take that 1 meter distance divided by that many copper atoms, 4.4 times 10 to the third, and we get a final answer here of 2.3 times 10 to the negative 10th meter. That's how far apart the copper atoms in this cube